everyone. I'm Dr. Castle, a metallurgist by profession, an expert in the field of quenching of steel and aluminium with wide experience in development and application of various quenching media across industries worldwide. I would like to welcome you on this journey of understanding quenchants. This tutorial is being developed to give you an in-depth knowledge of quenchants. My goal is for you to be able to achieve professional results as quickly as possible, with the expectation that the training will promote increased understanding of the subject. This tutorial is fully comprehensive. It covers A to Z information about quenchants. Whether you are an old hat or you are new to the world of quenchants, you are going to love and enjoy this tutorial. So let's see what is in store for you. Definition of quenching. General information on quenchants. Quenching oils. Water-miscible quenching media. And heat treatment salts. These are the topics we will be covering in this tutorial. Let's go ahead and get started. So, let's begin with the first topic, definition of quenching. First and foremost, let's understand what is quenching. Quenching is rapid cooling of steel from austenizing temperature, which is around 830 degrees Celsius to 910 degrees Celsius by immersing in a quenchant, which can be oil, polymer solution, gas, water, or even salt. By quenching, we can increase the strength of the steel. Various properties like hardness, yield strength, impact value can be achieved by proper quenching. That was a quick brief on quenching. Hope it was informative to start with. In the following topic, we will get into details about the quenchants. So, let us proceed further and understand more. Let us look at general information on quenchants. Let's have an insight on the various subtopics such as Hardcastle, Petrofer and quenching, physical and chemical data of the various quenchants, the quenching process including the vapor blanket phase, the boiling phase, and the convection phase. We will also discuss the effect of bath temperature on the quenching process, aging resistance, service life and consumption, the safety precautions required, maintenance and monitoring of quenchants, and finally, cleaning heat-treated components. Well, now we begin with the first subtopic under general information on quenchants, Hardcastle, Petrofer and quenching. The metallurgical properties of heat-treated steel components are primarily dependent on the following factors: austenitizing conditions, hardenability of the steel, and quenching process used. Well, to begin with austenitizing conditions, the austenitizing conditions like Hardening temperature. Furnace atmosphere. Hardenability of the steel. The hardenability of the steel, which mainly depends on the chemistry or grade of steel and percentage of alloying elements. Quenching process. The quenching process used, whether carburizing, through hardening, or induction hardening. Modern heat treatment processes are continually making new demands on quenching fluids, and Hardcastle Petrofer's extensive development programs ensure that our product technology is more than capable of meeting these new requirements. These programs are designed not only to improve the technical properties of our quenchants, but also to provide economic and environmental benefits. At Hardcastle Petrofer, we use the latest technology. We are constantly screening new raw materials for their suitability for use in quenchants, and our existing product range is reviewed continually to ensure that the best available technology is used. We also collaborate with equipment manufacturers and our valued customers for developing new products according to their specific need. By using this approach, backed by our in-house capability and know-how, we are able to offer the most comprehensive range of quenchants available today. Comprehensive range of available quenchants. Medium-speed quenching oils. Accelerated quenching oils. Bright quenching oils. Hot quenching oils. Vacuum quenching oils. Water-based polymer quenchants. Molten salt baths. And customized quenching oils. By having our own extensive development facilities and a complete range of products, we can ensure that the best solution is delivered to meet customers' needs. Many factors are important in choosing the most suitable quenchants. Hardenability of steel. Hardenability refers to the capacity of hardening or hardening depth in a steel rather than the maximum attainable hardness value. Alloying elements like magnesium, chrome, nickel, molybdenum, vanadium increase hardenability. Alloy steels have significantly higher hardenability as compared to the plain carbon steels. Hardenability of any steel is evaluated by Jomini end quench test. Component details, that is, component shape or geometry such as gears, bolts and nuts, bearings, steel bars, forgings of crankshaft, connecting rods, stub axles and knuckles. Metallurgical properties required like hardness, case depth, yield strength, impact values, etc. Furnace equipment. Bogie furnace, pit furnace, and sealed quench furnace. Post-treatment. Washing machine. Environmental issues. As many variables often have to be considered, it is important that a comprehensive knowledge of the quenchant is available. That is, Physical and chemical data. Quenching properties. Thermal and aging stability. Physiological and ecological properties. Okay, now we shall move on to discuss one of the most important aspects of selection of suitable quenchants: physical and chemical data. Important data for identification of quenching oils typically are viscosity, flash point, specific gravity. Let's understand the relation of viscosity and oil bath temperature. By maintaining the correct bath temperature, one can achieve optimum working viscosity of the quenching oil. When the quenchant temperature is too low, it can result in high viscosity, reduced agitation, and increased drag-out loss. When the quenchant temperature becomes too high, it can cause unnecessary smoke formation as well as increased fire hazard. Let's refer to the graph of viscosity versus application temperature of the quenching oils. Quenching oil temperature should ensure optimal viscosity, which is generally in the range of 5 to 15 centistokes. The red line indicates low viscosity accelerated quenching oil. The blue line indicates a medium fast speed quenching oil having high vaporization stability. And the yellow line indicates hot quenching oils. Importance of product flashpoint. It limits the application temperature range. Typically, the application temperature upper limit should be approximately 60 degrees Celsius below the oil's flashpoint. Specific gravity of a pure mineral oil can give an indication of its origin. However, it can be significantly modified by additives, and therefore, the quality of a quenching oil cannot be determined on the basis of its specific gravity. Let's catch up on the next topic, the quenching process. The quenching process. A quenchant is characterized primarily by its quenching properties, and these are difficult to describe in words. Descriptions such as severe quench or mild quench are of little use in technological era. The quenching process or cooling rates can, however, be studied using test probes such as nickel and nickel alloy probes using cylinders 12.5 mm diameter as per ISO 9950, or alternatively steel probes 3 to 80 mm diameter as per Meinhardt method, or a silver ball 20 mm diameter as per MPI silver ball method, or silver cylinders 8 or 16 mm diameter as per SETIM method. We use the IVF quenchometer for cooling curve analysis, which has an Inconel probe of 12.5 mm diameter. Usually, the cooling effect of a quenchant is shown by charting temperature versus time, or the rate of cooling versus temperature. The following graph shows the relationship between these two methods. We now look at the relationship between temperature versus time. The red line on the cooling time graph shows higher speed, as compared to the yellow line showing lower cooling speed of the product. Now we move on to the rate of cooling curve on the right side of the diagram. Here, the red line indicates the typical cooling characteristics of the faster quenching oil, as compared to the yellow line, which depicts slower cooling rate of the quenching oil. We now move on to the study of the three phases of quenching. A vapor blanket is formed on the component immediately after immersion in the quenchant. This vapor layer acts as an insulator because of its low thermal conductivity, and therefore the cooling rate in this phase is low. The duration of this phase depends essentially upon the quenchant's composition. Our accelerated quenching oils have a very short vapor blanket phase, and in this respect are superior to most other quenching oils. A short vapor blanket phase is not only necessary to avoid undesirable pre-transformation microstructures, but it also ensures a steady lowering of temperature on the entire surface of the component, thus minimizing thermal stress and distortion. After a period of time, depending upon the quenchant and component geometry, the vapor blanket starts to break down and the boiling phase begins. Heat is conducted away at an increasing rate by evaporation of the quenchant at the component surface. The rate of cooling reaches its maximum, and as the surface temperature falls, boiling becomes weaker and finally ceases. In the last phase of cooling, heat is conducted away only by convection. Consequently, cooling in this phase can be significantly affected by circulation of the quenchant. A high degree of cooling in the convection phase will result in deeper hardening of the component. Well, for evaluation of the cooling curves, the following points are therefore important. Duration of the vapor blanket phase, temperature range of the boiling phase, the cooling rate during the convection phase, and the temperature at which it begins. A shorter vapor phase gives fast and homogeneous cooling of the entire surface of the workpiece. Wide boiling phase gives good heat extraction in large diameter components. Cooling in the convection phase can be influenced by circulation of the quenchants. Significance of maximum cooling rate. The maximum cooling rate can be used to compare various quenchants. The relation of the steep slope of temperature versus time curve and its position in relation to the time-temperature transformation diagram is of utmost importance. The green lines show the typical time-temperature transformation diagram of a plain carbon steel grade. The cooling speed curves of two different quenching oils are shown in red and yellow. The red line shows quenching oil having a short vapor phase, and the yellow line indicates the quenching oil having longer vapor phase. A short vapor blanket phase is necessary when quenching low alloy or plain carbon steels, as only a few seconds or, in extreme cases, fractions of a second are available for the temperature to fall below the critical temperature range of approximately 600 to 500 degrees Celsius. If this requirement is not met, undesirable soft structures such as bainite, pearlite, trustite, and possibly ferrite occur, resulting in lower hardness. For the hardening of alloy steels, where the TTT curve lies further to the right, the duration of the vapor phase is less critical. But one should also consider that uniform cooling of the surface reduces thermal stress and distortion, as discussed earlier. In the following topic, we will learn the effect of bath temperature on the quenching process. The graph shows the effect of average cooling rate when the temperature of the job is in the range of 800 to 300 degrees Celsius, measured in degrees centigrade per second, plotted against the quenchant bath temperature. For all practical purposes, quenching oils do not change their cooling characteristics when their bath temperature remains within the recommended working range. Only extremely low or greatly elevated temperatures lead to lengthening of the vapor phase, and thus a change in the performance of the oil. However, aqueous or water-based quenchants are affected significantly by bath temperature. This is caused by the much smaller difference between the working temperature range and the boiling range of aqueous solutions in comparison with oils. Water boils at about 100 degrees Celsius, whereas oils boil from about 300 degrees Celsius upward. Consequently, when aqueous media are being used, bath temperatures must be kept constant within relatively narrow limits. The graph shows the influence of bath temperature on the quenching performance of several quenching fluids. The average cooling rate of water, additive salt in water, and up-concentration polymer quenchant reduces as bath temperature increases. Whereas, in the case of low-viscosity accelerated quenching oil and hot quenching oil, the average cooling rate remains almost same throughout its operating temperature range. Let us once again review the influence of bath temperature on the quenching properties. For quenching oils, the bath temperature has insignificant influence when operated within its recommended viscosity range. For polymer solutions, bath temperatures have a considerable impact on quenching properties. This can be used advantageously when quenching tool or die steels, and slow cooling is required. While quenching in water, the temperature of water bath has a distinct effect on the quenching characteristics. The control of bath temperature plays a significant role in ensuring uniform quenching characteristics throughout the quenching cycle. For control of the bath temperature, we can consider heat balance calculation as shown, where the formula indicates heat input from the metal is transferred to the quenchant. It can be used to design the cooling arrangement required to maintain a constant temperature. The temperature of the quenching oil must be maintained within the recommended range, as it can significantly influence the life of the oil, drag-out loss, and distortion of components. Various types of heat exchangers like shell and tube, plate type, forced air-cooled can be used for control of temperature. The screen shows a typical schematic of a plate-type heat exchanger through which hot quenchant is cooled by circulation through the heat exchanger. Now let's move on to a discussion on the aging resistance, service life, and consumption of quenchants in the process. Resistance to evaporation has a considerable effect on consumption and thus on oil bath economics. Experience has shown that on batch quenching, probably more oil is lost through evaporation than through drag out by the components. Aging resistance is, however, of the greatest importance in determining the economics of any oil bath. Oils having poor oxidation resistance will form a sludge after a short period in use, and this normally results in deposits in the cooler, the coldest place in the quenching bath. Ultimately, discoloration appears on the surface of the treated components, which is either difficult or impossible to remove. At this stage, replacement of the oils is unavoidable. During the development of our quenching oils, we have placed great emphasis on their resistance to oxidation aging by using highly stable base oils and, in many cases, sophisticated proprietary additive packages. The image on the left shows quenching oil having good aging resistance after an oxidation aging test. The image on the right shows quenching oil with poor aging resistance after an oxidation test. Now, let us discuss the advantages of using a quenchant having stable parameters. The high evaporation stability of oil helps in reduction of smoke and also the consumption due to lower evaporation. The good oxidation stability of the oil provides better service life and helps reduce sludge formation. The oils having high thermal stability significantly reduces smoke and helps retain typical quenching properties for a longer period. Several important points need to be observed when using an oil bath in order to achieve the optimum working conditions. In order to keep the thermal loading within limits and also to avoid severe variations in the working temperature of the bath, a relationship between the weight of the batch or hourly throughput of the furnace and the volume of quenchant must be maintained. Consequently, the following values can be used as a guide to the relationship between the weight of quenching oil and the gross weight of the batch to be quenched. Open oil baths 10:1. Sealed furnaces 10:1 to 7:1. Hot quenching oils used at their highest temperatures 10:1 to 15:1. These values can also be used where quenching of small batches at short intervals takes place, and the hourly throughput of steel is then used in the calculation. Now we see the effect of loading pattern. This relationship depends upon the conditions of the use of the oil and upon the size of the components. Larger components which take longer to cool cause a lower thermal loading to the oil bath than tightly packed batches of small components which give off their heat rapidly. The cooling and the heating elements of the heat exchanger should not be made of copper, as this acts as a catalyst in the oxidation of all mineral oil products. The level of agitation in the system must not be excessive, such that air is drawn into the oil. This condition will result in foaming and increased oxidation of the oil. The heating area loading of the heating elements should be limited to about 1 watt per centimeter square. If a higher loading is used, good movement of oil in the area of the elements must be maintained to avoid overheating. The life of water-miscible quenchants is usually limited by several factors. In the case of induction hardening operations, the solution has to be replaced after periodic intervals due to the effects of contaminations from previous processes. The thermal loading can also take its toll in the long term. In view of this, and the need to control the concentration of solution, monitoring is required for polymer quenchant solutions. Now, we need to deal with the most important aspect, safety precautions. Let's have a brief discussion on it. While operating quenching baths with oils, we need to exercise certain safety precautions to avoid quench fires. Ingress of water into quenching oil bath, typically through a leaking cooler or as a condensate, does create a special hazard. As little as 0.1 to 0.3% water contamination can considerably increase the fire hazard, as well as significantly change the quenching characteristics of the oil. Quenching oils are combustible liquids, and in the quenching process, the temperature of the components being treated is usually well above the flash point of the oil. Simple precautions are required so that there are no fire hazards in practice. Immersing the charge completely in the quenching oil is essential to avoid fire hazard. Maintaining the quench oil level to ensure sufficient head of quenching oil above the surface of the components is also recommended. It is advisable to turn on the agitation of quenching oil before start and during the quenching cycle. Contamination with fire extinguisher can change the quenching characteristic and other properties of the quenching oils. Drag-in of soot in the quenching oil can lead to stains on the component surface. Now, let's take a look at maintenance and monitoring. Aqueous quenchants must be carefully monitored with respect to both the operating temperature and the concentration of the solution. Relevant instructions have to be carefully followed to ensure successful result. Under normal operating conditions, quenching oils do not require regular monitoring. Attention should, however, be paid to ensure the working temperature of the oil is maintained and that the temperature never exceeds one which is at least 60 degrees Celsius below the oil's flash point. The oil should also be regularly checked for water contamination. We recommend checking oil baths at least annually and water-miscible quenchants at shorter intervals depending upon the operating conditions. Well, let me now brief you on cleaning heat-treated components. When water-miscible quenchants are used, post-cleaning of the heat-treated components is often unnecessary, even before tempering. However, when high concentrations are being used, rinsing of the components is recommended. Hardcastle Petrofer's quenching oils will produce hardened components with a bright finish, provided, of course, there was no prior surface oxidation. The components are suitable for further treatment, such as electroplating, without problems. Oil residues do not burn into the surface of the metal and therefore can be easily removed. Removal of quenching oil generally requires the use of hot aqueous cleaners or use of water-washable quenching oil. Degreasing with solvents in a soak tank or in vapor is also possible. the hot cleaner chosen should be formulated to provide rapid release of the quenching oil so that it can be easily removed from the wash tank. Hardcastle Petrofer has developed High Clean for this purpose, thus enabling wash water to be used for longer periods with savings in the disposal costs. For removal of separated oil, the use of weir systems or oil skimmers is recommended. Even emulsions from water-washable quenching oils are destabilized when small quantities of High Clean, 0.5 to 2%, are added to the washing water. Centrifuges also enable very good oil separation from the wash and can be used for both conventional and water-washable quenching oils. It is essential to exercise certain precautions to avoid negative influences in the cleaning process. When agitation is inadequate, it may influence the cleaning of parts, particularly when the parts to be cleaned are immersed in the bath in a tightly packed condition. Care has to be taken to ensure oil residues on the parts are properly cleaned by the use of suitable cleaner, as otherwise these residues can cause smoke formation during subsequent tempering processes. The health of the cleaner bath is required to be ensured by proper skimming, so that the parts after cleaning do not get coated again with the oil layer floating on top of the cleaner bath. Well, we come to the end of general information on quenchants. Hope it was an informative session. We are now going to begin with the third chapter, Quenching Oils. In this chapter, we will discuss our range of quenching oils, which includes medium-speed quenching oils, medium-fast-speed quenching oils, fast-speed quenching oils, quenching oils, and special quenching oils. Let's proceed and discuss each category of the quenching oils listed. Let's continue the discussions on the medium-speed quenching oils. Medium-speed quenching oils are recommended for general-purpose applications. These oils are formulated with high-quality base oils, additives for high oxidation stability, and speed improvers. They offer normal quench severity, which makes them suitable for hardening of low and high alloy steel grades. They are normally used in open quench tanks due to their higher oxidation stability characteristics. We can summarize the typical applications for use of quenching oils as hardening of automotive forgings, hardening of heavy forgings, hardening of bearing races, quench hardening of tool steels, hardening of martensitic grades of stainless steel, and many such general-purpose quenching applications. We now move on to the popular products from Hardcastle Petrofer's range of quenching oils. The products listed in the table are cold quenching oils, where the oil temperature is normally maintained in the range of 30 to 80 degrees Celsius. These products are mainly identified as High Quench N, High Quench 42M, High Quench M, High Quench 311 based on their kinematic viscosity, and Flashpoint measured by Cleveland Open Cup method. Now let's move on to discussions on the medium fast speed quenching oils. Medium fast speed quenching oils are formulated to enhance quenching performance. These oils are used mainly in hardening of plain carbon and alloyed steels. These oils are normally used in continuous furnaces and sealed quench furnaces. As the category name shows, the quenching speed of these oils is in the medium range, providing a wide scope of the applications across the various steel grades, parts geometry, quenching systems involved, etc. A few typical examples of wide range of possible applications are shown in this slide. They are
hardening of high tensile bolts, screws, nuts, washers, etc.
hardening of hand tools, heat treatment of steel bars and sections, hardening of leaf and coil springs, hardening of case carburized parts including transmission gears and shafts, hardening of bearing races, hardening of automobile forgings. From the vast range of medium-fast quenching oils, three popular products, namely High Quench MF, High Quench MFA, and High Quench MF Plus, having different typical viscosity at 40 degrees Celsius and flash points, are shown. The temperature of these oils is maintained in the range of 30 to 80 degrees Celsius. To know more about quenching oils, let us learn about the fast-speed quenching oils. Fast-speed quenching oils have been especially formulated for use in sealed quench furnaces. They exhibit short vapor phase and high quench severity. Hence, the quenched parts in the batch are uniformly and rapidly cooled. These oils are therefore used successfully for low distortion hardening of large diameter and heavy transmission gears and parts where high core hardness is required, or for hardening of components of low or lean alloy steels. By virtue of the short vapor phase and high quenching speeds exhibited by fast-speed oils, these products are extensively used for cold quenching applications, mostly in furnaces where controlled atmosphere is maintained in order to achieve stable performance over a long period. The table shows some of the important fast-speed quenching oils widely preferred by many of Hardcastle Petrofer's customers. The wide range of viscosities offers customers choice to suit their demanding performance requirements. The recommended oil temperatures are in the range of 40 to 80 degrees Celsius. The next in line is the information on the mark quenching oils. Mark quenching oils are popularly known as hot quenching oils. Following the development of new additives, these oils can now offer better cooling properties and high oxidation resistance at higher operating temperatures. This allows new standards to be set for the operation of hot oil with respect to quenching speed, distortion control, service life. Optimum hardness and lowest distortion can be achieved because of the extremely short vapor blanket phase and the slow cooling rate during Martensite transformation. Hardcastle Petrofer's popular quenching oils are shown in the table. HighQuench MT650 is the most popular grade, having a typical viscosity of 65 centistokes. This product is generally used in operating temperature range of 80 to 120 degrees Celsius. HighQuench MT780 has a typical viscosity of 78 centistokes and can be used in the temperature range of 60 to 150 degrees Celsius. HighQuench MT1115 has been designed for operating under difficult application conditions, including open quench tanks. It has a typical viscosity of 112 centistokes and can be operated in the range of 80 to 180 degrees Celsius. HighQuench MT400 is preferred where the application calls for very low viscosity of the product. This product, having 40 centistokes viscosity, can be used in a vast operating range of 50 to 150 degrees Celsius. HighQuench MT1800 is a popular product for open tank quench applications and has a viscosity of 175 centistokes and can be operated in the range of 120 to 190 degrees Celsius under specified operating conditions. Let's take a quick look at special quenching oils. Hardcastle Petrofer has a wide experience in understanding the specific needs of the various applications and have well demonstrated ability and expertise in developing customized quenching oils. Some such special purpose oils are hot and cold quenching oils, bright quenching oils, water washable oils, tempering oils, vacuum quenching oils. As the name suggests, hot and cold quenching oils are specially designed to provide quenching properties of cold quenching oil and also of hot quenching. Customers such as commercial heat treaters prefer a single quenching oil to suit the varying requirements in the same furnace. They have a limited number of furnaces, but at the same time have to quench a wide variety of components and steel grades. The product HighQuench MT500HC has a viscosity of 50 centistokes and can be used in operating temperature range of 50 to 100 degrees Celsius. HighQuench MT780 has a typical viscosity of 78 centistokes and can operate in temperature range of 60 to 150 degrees Celsius. Our medium-speed quenching oils and hot quenching oils are also available with bright quench additives, which improve the surface finish of quenched components by preventing the soot deposits from sticking on the surface of the quenched parts. Typical applications are carburized components such as automobile gears and shafts in sealed quench furnaces, continuous furnaces for bearing races, fasteners. Certain applications have specific needs for quenching oils having inbuilt capability to be washed off by use of plain water after quenching. These quenching oils contain special additives to provide this feature. Hardcastle Petrofer has developed tempering oils, which are used in applications where oil is used as tempering medium instead of air in order to achieve desired metallurgical properties of the quenched parts. They are also used for parts to be preheated in oil medium before they are shrink-fitted. Hardcastle Petrofer also has an established range of vacuum quenching oils which have been developed with the following special properties in order to achieve spotlessly clean surfaces. They offer extremely high resistance to vaporization, low gas absorption capacity, rapid degassing capability, extremely high degree of purity. So friends, we have come to the end of the chapter on quenching oils. Hopefully, this session was equally informative as the previous one. Going forward, let's proceed with the fourth chapter, water-miscible quenching media, also known as polymer quenchants. In this chapter, we will discuss the following: development and usage of polymer quenchants and the two types of polymer quenchants, inverse solubility polymer quenchants, up concentration polymer quenchants. Let's proceed and discuss. We begin with polymer quenchants. We shall cover the following: development of polymer quenchants, advantages over emulsion, substitution to oil quenching, comparison to oil cooling rates, incombustibility. As has been shown, quenching oils cover a wide range of cooling performance, yet there is still a significant gap between the maximum achievable cooling rate of a low viscosity accelerated oil and that achievable with the ordinary cold water. Water-miscible quenchants, which fill this gap, are thus an ideal complement to the quenching oil range. Heat treatment operation can be carried out with these water-based quenchants, which would either be impossible or extremely difficult with oil. This particularly relates to spray quenching in induction and flame hardening processes, where a high degree of fire risk exists when using oil. Emulsions have historically been employed in these applications instead of oil, but unfortunately, they do not give the low cooling rates in the temperature range for Martensite transformation necessary to reduce or eliminate the danger of cracking. These cooling characteristics can only be achieved with polymer quenchants. As a result of our continuous development programs, we are today able to offer users a complete range of water-miscible quenchants which successfully covers the whole spectrum from oil to water quenching. Accelerated quenching oils can already be replaced in a wide range of applications as polymer solutions are available, which give comparable cooling characteristics. These solutions are therefore suitable for hardening alloyed quench and tempering steels and some tool steels, as well as for quenching components directly from forging. Water-miscible quenching media are today used to a high extent as a substitute for quenching oils. It must be realized that these products contain from 60 to 98% of water in the ready-to-use condition, the level depending on the concentration to be used for a given application. Due to high water content in polymer quenchant solutions, the cooling rates in the boiling phase are usually higher than the cooling rates in quenching oils. All water-miscible quenchants are of course incombustible and, in contrast to oil quenching, helps avoiding the risk from fume and fire. This is particularly useful when hardening forged parts directly from forging temperature and for interrupted quenching, that is, time quenching of components. Hardcastle Petrofer has rich experience of formulating and manufacturing polymer quenchants. The wide range of polymer quenchants available provide the users the choice of options to suit their performance requirements. These polymer quenchants can be used in a wide range of concentrations in water. This property provides the users with the flexibility to use the same polymer for quenching of a variety of steel grades and also for use in induction hardening as well as tank quenching applications. By careful selection of high-quality raw materials, the efficient performance is ensured. Hardcastle Petrofer polymer quenchants exhibit very high level of thermal stability, thus providing consistent performance over a long period. High-quality corrosion inhibitors, biocides, and defoamers help effectively control and maintain the quality of polymer solution in use. The use of water-miscible products can often be a new venture for customers, and therefore it is advisable to discuss applications thoroughly. This is obviously not so important with induction and flame hardening operations, where the use of water-miscible quenchants has been established for many years. However, for other applications, we recommend consultation with our technical service representative to make use of our extensive experience in this field. This is particularly important if a quenching oil is being replaced. Firstly, it is very important to provide the performance requirements of the applications to the technical representative of Hardcastle Petrofer. Secondly, it is also important for the user to provide complete information on steel grades, parts geometry to be quenched, the hardening process used, as well as the quench system. This enables our technical representative, who has extensive field experience, to recommend the most suited polymer quenchant grade. We shall now move on to a discussion about the two main types of polymer quenchants, namely inverse solubility type polymer quenchants and up concentration polymer quenchants. Inverse solubility polymers exhibit inverse solubility in water, that is, they are soluble in water at room temperature, but insoluble above the inverse solubility temperature, normally 65 degrees Celsius to 70 degrees Celsius. These polymer solutions reduce the quenching effect of water by virtue of the polymer in solution becoming insoluble at the inverse solubility temperature during the quenching process and plating out onto the hot surface of the component. The thickness of the insulating film formed varies with the concentration of the polymer in the original solution. When the component cools to below the inverse solubility temperature of the polymer solution, the film starts to redissolve completely, thus ensuring the drag out of the polymer to remain low. Hence, these polymer quenching solutions are very economical in use. Inverse solubility polymer quenchants are used in quenching baths, mainly for hardening low alloy steel grades, quench and tempering steels, which are difficult to harden with quenching oil, but which are prone to cracking with water quenching. They can also be used for induction and flame hardening processes. Inverse solubility polymer quenchants can be used for a wide range of applications. Quenching of forgings of low alloy and plain carbon steels for automobiles. For example, crankshafts, connecting rods, camshafts, etc. Quenching of steel castings. Quenching of bars, sections of low alloy and carbon steels. Hardening of hand tools, spanners, wrenches, tongs. Hardening of high-pressure cylinders and seamless tubes. Hardening of carburized or carbonitrided small parts in continuous furnaces, chain and bicycle components. Induction hardening of crankshafts, camshafts, gears, splines on shafts, slewing rings, axle shafts, velocity joints, etc. Inverse solubility polymer quenchants are also used for solution heat treatment of aluminium. Typical applications for aluminium are sheet panels and sections in the aerospace industry, castings and forgings used in automobile industry. For example, cylinder heads, engine blocks, alloy wheels. Hardcastle Petrofer has a major share of business in India for their inverse solubility type polymer quenchants. These quenchants are classified according to their respective kinematic viscosity at 40 degrees Celsius. We generally recommend the application temperature in the range of 25 to 55 degrees Celsius. Amongst the products shown in the table, HighQuench P11 and HighQuench P12 are used by a large number of customers in India for induction hardening as well as tank quenching applications. The two products, HighQuench P122 and HighQuench P21, are used where the application requirements are very demanding. Hardcastle Petrofer also has special grades of polymer quenchants which are used for solution heat treatment of aluminium parts, such as sheet panels and airframe section in the aerospace industry, and for castings and forgings of parts such as cylinder heads, engine blocks, alloy wheels, etc., used in the automotive industry. The new generation up-concentration type polymer quenchants provide an even more significant reduction compared to inverse solubility polymer quenchants in quenching speed when added to water at various proportions. Concentrations of 8 to 20% give cooling curves practically equal to those of quenching oils. Reduction of the quenching rate compared to that of water is achieved by the formation of a polymer film on the part surface during cooling. In the beginning of the cooling process, a thin polymer film ensures uniform collapse of the vapor blanket and the start of the boiling phase. With further cooling, an insulating film develops, and the thickness of the film varies with concentration. Its insulating effect ensures a controlled heat flow from the component into the quenchant. These polymer quenchants are used to treat steels of higher hardenability. For example, for quenching alloyed, tempering, and case hardening steels, and for hardening tool steels. Interrupted quenching of components is possible at any desired surface temperature. These polymer quenchants can be used for a wide range of applications. Quenching of open die-forged components like turbine shafts, seamless rolled rings, valve bodies. Quenching of bars, coils of martensitic stainless steels. Quenching of die steels, tool steels. Well, we come to the end of the 4th chapter. I hope you are going to take advantage of what you have learned in this chapter. Let's move on to the next chapter. Going ahead with the tutorials, let's proceed with the last chapter, Heat Treatment Salts. We will now cover the final topic of discussions, heat treatment salts. These are broadly classified based on their usage, such as austenizing, quenching, and tempering. We can offer the following salts: mark quenching salts, hardening salts, water additive salts. We will now take up the first type. Mark quenching salts. The various types of mark quenching salts available are classified as per their melting point and thereby their lowest application temperature. Generally, mark quenching salts are used between 200 to 350 degrees Celsius. The maximum possible bath temperature for these products is 550 degrees Celsius. However, at higher temperature, thermal decomposition of the salt increases rapidly. The quenching rate of these salts normally reduces by contaminants like carryover from hardening or carburizing salt baths, scales, or by carbonate formation at higher temperatures. These contaminants have to be removed by desludging the bath periodically. However, the quenching action can be enhanced by adding water in quantities up to 2%. Our range of mark quenching salts are high salt 1150. It is recommended for applications like mark quenching of critical components as well as for austempering process. For austempering application, specifically we recommend the use of high salt 1220, which has a higher melting point as compared to high salt 1150. High salt 2460 is used for quenching of high-speed steel grades at higher temperatures. Taking forth the discussion, let's discuss the next type of salts, hardening salts. These are normally used for heating the components to austenizing or hardening temperature. The salts can be selected depending on the operating temperature range required. Normally, from 500 to 1300 degrees Celsius. For the general hardening applications, we have three popular products in our range, namely High Salt 2550, High Salt 660, and High Salt 2670, having different melting points and application temperature range to suit the hardening requirements. High Salt 2840 is having the highest melting point in this category and can be used in application temperature range of 900 to 1300 degrees Celsius in high temperature hardening applications. We will now discuss the last subtopic, water additive salts. These are normally mixed with water to increase the quench severity. Water additive salts are used for hardening of plain carbon or free machinable carbon steels to attain maximum hardness. Water and salt combinations have unique ability to shorten the vapor blanket phase. Consequently, they can be used at temperatures of about 50 degrees Celsius, whereas the quenching action of plain water decreases significantly above temperatures of 20 degrees Celsius. Our range of water additive salts consists of High Salt WQA, which is nitrite-free, and High Salt WQS, which contains nitrite. So, my friends, we have come to the end of this tutorial and hope you have enjoyed it as much as I have enjoyed presenting it. We've spent a lot of time today understanding quenchants in depth. Well, let's see what all we touched upon so that we don't quite forget. We started off with understanding what is quenching, general information on quenchants, and then moved on to the different types of quenchants. We covered quenching oils, water-miscible quenchants, and also heat treatment salts. If you do have any more doubts, feel free to get in touch with me. You are always welcome. Hope to see you again. This is Dr. Castle signing off. Goodbye and good luck.